Hello everyone, welcome to my channel. This is actually the first lecture for the foundation design. I'm going to start with the quadratic equation, the importance of the quadratic equation in foundation design. I want to show you where in my book, because I'm writing this book, the foundation design in concrete structure. I'm going to show you in a part of the book that has always have the quadratic equation, so that you can use the quadratic formula to solve for x if it is x, right? Here it is. I'll show you that first. After I'm going to show you the program, how fast it is. The program will solve the problem of the quadratic equation. Here you can see this is the content of my book. It's about 120 pages. There are two foundations that I designed here. Number one is the combined footing, and number two is the continuous footing. The reason why I choose combined footing is more complicated than rectangular or isolated footing. This is more complex, and also the other complex one is the continuous footing. Here you see here is the quadratic, always have quadratic equation right here. This is how to solve the reinforcement ratio, the P balance as we call it. So in here the reinforcement ratio balance is 0.009. It should be less than P maximum and is equal to 0.75, 0.33. So I'm just going to show you this part of the book, that when you design a foundation there's always a quadratic equation when you use the ultimate strength design formula. Here's this part of the book, and there are about 0 pages. There's 94 pages. There's about 120 pages for this, for two foundations. I'm going to show you some parts of the book. Okay, this part here is how to calculate the transverse reinforcement space to be in the foundation. This is the theoretical width of the transverse reinforcement to be laid out. That is the space where the transverse reinforcement is to be placed. Listen there. This calculation here is the calculation of the clear distance of between reinforcement. The ECI code gives you, or give me, or give us a minimum of 40 millimeter in between, clear distance between that. So when you have the reinforcement design already, you gotta calculate that. See if it's more than 40. The minimum is 40. You cannot have smaller than that. Okay? Because or else the foundation will be so congested. If you have no room for the clear distance of 40 millimeter, therefore you have to remove the some of the transverse reinforcement, usually 3 or 2, and then bundle it with the other one. Like see here, I have to remove it here and put it over here, equally distributed. Okay, so some of the reinforcement will be bundled when you have a very close distance, less than 40 millimeter. Okay, this is the sign of longitudinal reinforcement. That's the bottom of the column. And this is the continuous footing that I designed also. This is the shear moment diagram, how it's gonna look like. The calculation of this also is lengthy. I include the calculation of all these shears and moment in the very last portion of the book. All I have here is the actual shear and actual moment so that you can use it in design. There's no point of typing it over here. You can review it later after the end of the book. I put it there. So that's chapter 7, design of reinforcement bars. And here's the structural analysis for the foundation, and this is about the beam shear. There are two shears that you gotta check the foundation. Number one is the punching shear and the beam shear. Compare the result between the two, and the largest one will govern. Okay. This is continuous footing, right? There's another footing here. There's another column here. But when you analyze it as a square. See, W is equal to B. Okay. Whatever you get distance there is equal to that distance there. Analyze it like a square, because the reinforcement is only up to here for transverse. Okay, so you gotta determine that. W equals B. And this distance here is the column, the width of the column plus D. The calculation of designing the D, that's how deep is your foundation. That is massive. Okay, before you get that D, there's a lot of calculations. Okay, I'll show that later on if I have time. I'm just gonna have I'm gonna show the preview of this book, page 85. Okay, this is the structural analysis for the footing, and this is analysis for the beam shear. You gotta have beam shear and punching shear. Analyze both, then compare. This is how to get how deep is your. There's a lot of calculation here too. So this is how can you design how deep is your footing. Okay, one beam shear and then another punching shear right there on the top. In the punching shear, this is the area of resistance, the area of the strength, the resisting strength of your section, foundation section, and this is taken from this right here, that perimeter there. When you draw an elevation and open that, this is exactly what it is. So this is the total perimeter of the punching shear multiplied by how deep is your foundation, and that is the area of resistance, and multiply the allowable for concrete, allowable stress for concrete, and you get the capacity, the load that this foundation can carry. Okay, this is the attack, how you attack the punching shear there. Analyze this like this, and again the analysis for punching shear is right here, and here is the continuous footing. This is the same building that I am working. There are 6 columns here. This is a transverse direction. The worst of this building is the longitudinal direction. There are about 12 spans. This is transverse, the short direction of the building. Here's a uniform column loads right here. They're the same, and the exterior column is 1/2 of the load of the exterior column. and you design the footing. These are the two rows of transverse reinforcement direction. You gotta check the overlapping. See, make sure these two projecting footing right here, both sides. Make sure that these two doesn't overlap. You have to avoid overlapping between the two. And this is taken from the first book, preliminary design of the book, to determine the final column load that is used for design. Before you get this, there's a lot of work. You got to design the slab, the beam, the girder, and the column. You got to design that and then calculate the weight, all of that, from the roof all the way down to here. This is the final column load that transfers the load to the foundation, and that is now you can design the foundation based on this load here. All the way here, from here, there's a lot of work, there's a lot of calculations. Final column load, let's see there. And this is the actual strip of tributary area where the column carry all these loads. These are the loads that this column is carrying going to the foundation design. So each one of them you have to calculate them. Okay, the sizes of the structural member here. Without the size you don't know the dead load, the weight of the concrete. And that's the most important load that the foundation is carrying. Never mind the live load. Sometimes there's no live load there. Live load is like a moving load. Sometimes it's in there, sometimes it's not there. What is the static load that the foundation will be carrying throughout its life are all these concrete loads here, floor by floor, column by column. Once you reach here, you're ready to design the final column load. Then you can design the foundation design. Okay, this is the actual strip of the tributary area during the analysis, how to calculate the load of each floor and transfer that load up to here. All this above is carried by this column. The column on the top, third floor right here, is smaller, and as you go down it becomes bigger and bigger and bigger and bigger. This is the largest of all this column here, okay, according to my design. Here are calculations right there. This is the slab, design of the slab. I included the slab here because, so you can see how the preliminary design is important and how the preliminary design process is done. Okay, this is tributary area, intermediate beam. This red color there are the intermediate beams. The intermediate beam is not framed to the column. That's why it is called the intermediate beam. It is framed to the other beam. And when you frame, when a beam is carrying another beam, that is called a girder in the proper terminology in structural engineering. And this is the beam, and that's the girder. Girder is the father of all beams. Okay, the intermediate beam is framed to that beam, and that beam is called a girder. Any beam that carries another beam is called a girder. Alright, and the girder here transfers its load to the column right here, and the girder, all the girders transfers to the column. So that's the intermediate beam there. and this is tributary area. This is where the strip, remember that picture there, so you can visualize the actual load of the final column load by just making a drawing, a complete diagram of all the loads for that particular column in the basement going to the foundation. Tributary area is important. Okay, that's for the slab. It's a fixed end, so use this formula here, WL squared over 12. And here's the details of how the load is calculated for the slab all the way down. And that load here is from this frame here. This is the typical floor framing plan for this building. And here's the longitudinal span I was talking about, and here's the transverse. I designed it right here in this direction. This row here I designed for the foundation. Now here's the origin of these loads. This is part 2. Oh my god, we're not even in part 1. I'm just gonna share the part 1. Okay, here's the final and complete combined footing, exterior column right here, and the interior column. Reason why I use combined footing is it's more complex to design compared to the square isolated footing. So that's why, you know, you can learn, right? There's nothing to learn in designing the square footing and the rectangular footing. Alright, so this is more complex, so it's good to write a book about this. So that's why I'm writing this book. That encouraged me. This is the transverse direction of the combined footing, and this is the exterior column side of the combined footing. I cut there in half because it's too big. It won't fit here. And these are all the details. To get all this, the sizes, distances, it's a massive calculations. It's not gonna fit in like a 4 hours video if you have to video it. So I just show you the layouts and how the foundation looks like. See here, this is the bottom reinforcement, longitudinal reinforcement. This is in a long direction, and the transverse direction, don't make mistake here, transverse direction is always on top of the longitudinal direction. Okay, to solve for this length here, where to place all this transverse direction, there's a theory for that to get this 1 meter, and it's another calculations there that's long. And here, this is the longitudinal direction below the column. It's always the bottom of the foundation. It's always placed there, the longitudinal and the transverse reinforcement. And the cutoff point here, the lap between these two, see, you cut here, there's a lap distance here of it's not 75 millimeter actually. That 75 millimeter there is the concrete covering. The lap distance is 1.5 feet. Okay, and see 16 pieces there, and here the transverse, the longitudinal is 16 as well, transverse 13. And there's a lot of calculation before you get all these details, because before you can complete this foundation. This is the foundation under the exterior column. Next, here are all the calculations there. This is the structural analysis, how to get the load and to design the reinforcement of the foundation. You have to have a proper layout of the analysis so you can look at it if it's correct or not. And here's just the section telling you that that column is section XX and in this direction, and section double X is in the very long direction. Distances of the reinforcement bar. The minimum distance, clear distance between two reinforcement is 40 millimeter. That is the very minimum. You cannot go less than that. Reason for that is for the aggregates to flow in between, or else you're gonna have a honeycomb. If you get stuck, there's a hole there, and therefore the strength of your concrete is compromised. So that's why the code gives you the minimum distance, so that and you can use a 1.5 aggregate or less, so it can easily flow here. When you pour the concrete, there's no void. That is why we have 0.04, that's 40 millimeter in between. If by any chance your distance here is too small, less than 40 millimeter, therefore you have to remove 1 bar or 3 bars and then bundle it with the other bar. I'd like to put in the middle and both ends. Alright, when you remove a bar from the actual supposedly placement of the bar, you have to remove at least 3. Remove the 3 and bundle on the other bar on top of it. Okay, to bundle it, sometimes we use welding or just tie it with the with a wire, the tie wires, so that you can have a clear span. It is very important to have this clear distance here checked first before pouring the concrete. That is one of the most important in the inspection of reinforcement. When you are an inspector, you have to look at that. Here is the transverse direction. Here's how it looks like. See here, this is the longitudinal bar. This is the bottom bars, and this 0.9 here is how deep from the top to the centroid of the reinforcement, longitudinal reinforcement. To get this 9 meter here also is a lot of calculations to be done. And okay, this is a good part. And you have to calculate the centroid of the transverse as well. Okay, reason why you gotta use that in your design. Those distances are important in designing the reinforcement of the foundation. Here's okay, this important part right here I'm gonna explain. There's the column, there's a dowel. The dowel is larger than the column reinforcement. The vertical reinforcement for the column, you might know or you may not know, this reinforcement doesn't go through the foundation. It is cut on top of there. Okay, you think it goes there? No, you have to cut it there, and there's a dowel going to the foundation. These dowels, there are 4 of them on minimum. These dowels are bigger than the vertical reinforcement of the column. Okay, and there's a transfer of load here. The load from the vertical reinforcement is transferred to the dowels and going through the foundation. Alright, and this distance here, the projecting distance here from the top of the column, the foundation, that distance there is 30 times the diameter of the dowel. Okay, the diameter of the dowel is calculated the total area, cross-sectional area of the column reinforcement, total of that. You divide it by 4 if you want 4 dowels, so that you get the sizes of the dowel. And here in the bottom, don't forget this, the bottom tie bars for the column, tying up the column and the column vertical reinforcement and the dowel, you double the tie here. Right? The tie sizes here, column ties, column vertical ties, is 18 millimeter vertical ties, and the minimum distance between the ties there is 300 millimeter on center. Alright, so 4 dowels minimum per square column. Minimum reinforcement is 4. For rectangular column, minimum reinforcement is 6. Okay, I use square column here. It's 500, I think, by 500. What else are you gonna distance here? Yeah. So this is the transverse direction. When you cut in transverse direction, the longitudinal right here is in cross section, and here's the transverse bar here, length. Again, this length here, how you cut this bar, how long is this bar, is also have a theory and calculation for that. What else? Okay, here's the larger column. The interior column is larger than the exterior column. This is how the dowel looks like. This projection here is also the same as that. Okay, you gotta calculate that it's 30 times the dowel diameter, so you have that projection there. This here are the distances, transverse to the centroid and the longitudinal as well. The concrete covering, do not forget that. Minimum concrete cover before you install the reinforcement is 75 millimeter all around, same. And also, according to the code, the foundation is like a slab or a beam. A slab on the ground and beam on the ground. And according to the code, in the design of beam, of course it's the same as the footing. When the beam is from 24 up to 36 inches, that is 2 feet, from 2 to 3 feet, you have to provide a web reinforcement here in between. When you have that deep 24 to 36 inches, the foundation therefore will be provided stirrups. This is the stirrups, the vertical bar, and if it's like 2 to 3 feet deep, this is about 3 feet, it's 0.9. So then I provided stirrups right there. And then one horizontal web reinforcement. This is a web reinforcement right here, the vertical, 3 of them there. This is the most critical part of the foundation because this is open here, there's no column here. It's gonna shear off right here. Never mind here, it's not gonna shear there, there's a lot of concrete here. But how about here? So that's why according to the code, thanks to the building code, right? When a beam is more than 36 inches, more than 3 feet, you gotta provide two web reinforcement, horizontal web reinforcement. If this is like 3.5 feet, you gotta have two here, two horizontal web reinforcement. Web reinforcement means stirrups. This one here is a vertical ties, vertical